In this video, we'll prove that 1 is the smallest integer greater than 0. So recall we have as an axiom of the integers that 0 is not equal to 1. And we've proved in an earlier video that 1 is greater than 0. But 1 could be way up there. But it's not so. Here we'll prove that 1 is actually the smallest integer greater than 0. So the proof is based on our previous result again that 1 is greater than 0. And we'll use the following two axioms of the integers. The fact that if you have a non-empty set of integers that's bounded below, then that set of integers has a minimum element. And we'll use the fact that there are no zero divisors in the integers. So if the product of two integers is equal to 0, then one or both of those integers is equal to 0. Okay? So here's a precise statement of our theorem. Let's suppose you have a set A that consists of all integers k that are greater than 0. Then our claim is that 1 is the minimum of the set A. So let's take A to be that set. So A again is the set of all integers that are larger than 0. Now we proved earlier that 1 is greater than 0, so we know that 1 is actually an element of that set. And it's clear that 0 is a lower bound of that set. So if x is an element of A, then by definition 0 is less than x. Okay, so that makes 0 a lower bound of A. So what we have is we have a non-empty set of integers which is bounded below, and therefore we know it has a minimum. Okay, let's call that minimum element m. So we know m, the minimum, is an element of the set A, and we know that if x is any other element of the set A, then m is less than or equal to x. Now, in particular, since the minimum m is in the set A, we know 0 is less than m. And since 1 is in A, we know that the minimum has to be less than or equal to 1. Okay, so putting those facts together, we get that 0 is strictly less than m by virtue of m being in A. And by virtue of 1 being in A, 1 is greater than or equal to the minimum, so we have 0 is less than m is less than or equal to 1. Now m is bigger than 0, so we can multiply by m and preserve inequalities. So if we multiply through by m in that inequality, all the inequalities will stay the same, and we'll get 0 is less than m squared, which is less than or equal to m. Okay, so maybe you can see where this is going. M squared is an element of the set A, okay, because it's greater than 0, and so it can't be any smaller than the minimum of A. In other words, we have to have that m is less than or equal to m squared. The minimum of the set A has got to be less than or equal to m squared. And so we know that m is less than or equal to m squared is less than or equal to m, and that implies, by trichotomy, if you'd like to use it, m squared is equal to m. Alright, so we know the square of m is equal to m, so we're pretty close to concluding that m is equal to 1. We can't quite divide by m because we don't have that defined yet, and we don't have that defined in the integers. But we can add the additive inverse of m to both sides to give us m squared minus m is equal to 0. Then we can use the distributive property to pull out the m, and that gives us that m times m minus 1 is equal to 0. And this is where we use the fact that the integers have no zero divisors. So we know that the product of m and m minus 1 is equal to 0. So the fact that z has no zero divisors implies that one of those two elements of the product is equal to 0. Either m is equal to 0 or m minus 1 is equal to 0. Okay? But, of course, we know that m is greater than 0. And so it's not equal to 0. So the other one has to be equal to 0. That is, m minus 1 has to be equal to 0. And that, of course, implies m equals 1. So we've just proved that 1 is the smallest integer greater than 0. And that concludes this video. Thanks for listening.